Okay, hello, good morning. Do you have any questions before we start this lecture? Actually, it was very warm in like 3 days ago, but now it's very cold. So that's why I have my jacket in my office. Up to last time, we discussed the so-called moment curvature relation. Here, if I revisit the relation here, and then our bending moment, internal bending moment is equal to the flexure rigidity times the second derivative of the deflection, the measure of lateral displacement of the beam. And then make sure that for the small deformation problem, the second derivative of deflection is approximately equal to the curvature of the beam. Please make sure that this relation is only valid in a small deformation linear elasticity. But even in linear elasticity, if the case is not in small deformation problems, then the curvature is not equal to it cannot be approximated by the second derivative of deflection. The actual expression of the curvature is much more complicated, so please make sure about it. And then here we have a new constant for the geometry. We have the second moment of inertia. The second moment of inertia is integration of the cross section of the y square. This is the second moment of inertia. And then the last time, I wonder if you remember when we discussed polar moment of inertia, in the chapter of torsion problem. In torsion problems, we had a quantity called polar moment of inertia. The polar moment of inertia is equal to sum of the second moment of inertia in x with respect to x-axis and the second moment of inertia with respect to y-axis. That was the polar moment of inertia, isn't it, right? So please try to make a connection between different quantities. All right, so today we're gonna talk about the normal stress. By the way, so before we talk about normal stress, and last time we also discussed how to determine the neutral axis is here, right? Please make sure that the key point regarding the neutral axis is what? The condition for beam problem, the integration of all the normal stress over the cross section is equal to 0. This is the key point. Then because we have only single material and a single curvature, that's why these two are cancelled. So finally we have this equation, isn't it? And then if you using a new some reference coordinate, because we don't know the position of neutral axis yet before we satisfy that quantity, then we can change this equation into this equation. That's why the position of neutral axis measured from the reference position is given by this expression. So this is very important to determine the position of neutral axis. So if you don't like to choose the bottom fiber as the reference axis for the calculation of neutral axis, then maybe you want to use the top fiber. Okay. So even if you choose the top fiber as the reference position for the calculation of the neutral axis, you must have exactly same conclusion. Okay. And then for the detailed derivation, please take a look at my last lecture video. Okay, today let's talk about how we calculate the normal stress development. And please make sure that when we in the last lecture note, what the internal bending moment was defined as what the small forces over acting on cross section area, and then we want to calculate the moment contribution, isn't it? Okay, this is the relation between the normal stress and then normal stress and the bending moment. So if you put instead of stress, the elastic modulus and curvature, elastic modulus and strain, and the strain is the further given by the curvature times y coordinate, then we would have the second moment of inertia, isn't it? So using this relation, so we'd like to investigate the information of the normal stress. So here we already know how the normal stress would distribute over the cross section, because look at this. The strain distribution is equal to minus of curvature times the y coordinate. The strain is linear with respect to coordinate, and then which means, to calculate the stress, what do? Using the Hooke's law, we multiply the elastic modulus here, isn't it? That becomes the stress. So the strain is linear, and the strain is proportional to the normal stress by means of just a single coefficient in the case that we have a single material in the cross section. Then the distribution of normal stress is also linear. Must be, isn't it? Okay? So please, don't forget that aspect. All right. So now we're gonna derive so-called the Flexure formula, 휨 공식. Flexure formula for the normal stress. By the way, I have error. So in this morning, probably my TA uploaded, corrected version of my lecture note. So please correct in this way, okay? Okay, so note that the analysis procedure is always same. Okay, I'm talking about exactly same story from the start of my lecture, this class, and until today. So first we have defined the deformation system. So we start from the deformation, and then what? In the next step, we need to calculate the strain by the comparability, deformation and comparability. Once you have strain, then we calculate the stress using the material law, and then we integrate the stress to obtain the moment, isn't it? Calculate the internal forces by the equilibrium condition. The flow of analysis is always same. Not just limited to this class, the mechanics of materials class, and also other structural engineering classes, and then also the geotechnical engineering classes. This flow of analysis is always same. What if you have inelastic material? In the case of inelastic materials, this part should be changed to the inelastic function, such as in the case of elastic material, the stress is equal to the elastic modulus and strain. But if you want to use inelastic material, stress is the function of strain and other parameters. Okay, so we have an inelastic version of this behavior. And then let's say, okay, this is the constitutive relation. The normal stress should be given by the elastic modulus times the strain measure. This is the Hooke's law, isn't it? Now let's plug the information of the normal strain into the place of epsilon x. So we already know that in the last time discussion, the strain is proportional. Just simply you remember in this way. In the case of slender beam, okay, thin beam problem, the strain is proportional to positions, linearly proportional to position, measured from the neutral axis. Okay, that's the key point that you shouldn't forget. And that means strain, mathematically strain is proportional to y coordinate, and then we need a proportional coefficient to put the equality sign, isn't it? The proportional coefficient is the curvature. That's how you memorize this equation. So then my normal stress is given by the elastic modulus times the minus of the curvature and the y coordinate. Okay. So now let's revisit the information of the moment and curvature relation. So the moment, the internal bending moment, is given by the flexure rigidity and then the curvature, isn't it, right? So let's rearrange this equation with respect to curvature. Curvature is, by the way, curvature is not k, it's kappa, Greek letter, okay? The internal bending moment is divided by the flexure rigidity. Okay? So now let's plug the information of the curvature into here. That's why we have this equation. And the elastic modulus is cancelled here. So finally we have normal stress is minus of the bending moment times the y coordinate divided by the second moment of inertia. So you'd better memorize this equation. And this equation is very useful when you check, the development of normal stress in beam problems. So we use this equation in many different places, even in the engineering practice. In many cases, for example, we can simplify our problem into simply supported beams or cantilevers in many different cases. So in that case, we want to check the stress development using a simple consideration. Okay? So memorize this equation. So now let's check. Let's discuss the characteristics of this equation. So if you look at the terms, we have three different variables regarding the calculation of normal stress. The first one is bending moment, and the second one is second moment of inertia. Look, the bending moment is what? The bending moment is representative value for the cross section, isn't it, right? And then also the second moment of inertia is what? The measure of the geometry of the cross section. So which means for a beam section, these two are fixed or constant, kind of constant. That's why our normal stress in the x direction is given by minus of bending moment divided by second moment of inertia. So this is a parameter. And then y coordinate. Okay, this is y parameter. So normal stress, y coordinate, sorry. Normal stress is proportional to the y coordinate. And then the proportional coefficient, we have a constant proportional coefficient here. So then maybe it's easier to memorize this equation. Okay, normal stress is proportional to the y coordinate measured from the neutral axis, and then we have a proportional coefficient. So which is what? Of course, the magnitude of normal stress must increase for greater bending moment. That's why it must be proportional to the bending moment. And then if the cross section is bigger, then my normal stress gets smaller, isn't it? So that's why it is inversely proportional to the second moment of inertia. Is it clear? Now let's talk about an example here. So we have a rigid cylinder. Okay, we have a rigid cylinder here, and then a wire is placed around the rigid cylinder here. Okay, and then here we need to determine the bending moment and the maximum bending stress sigma max in the wire. Okay, so let's check one by one. The problem says that in this example, so we need to calculate the bending moment, isn't it, right? How do you calculate the bending moment? The flexure rigidity and the second moment of inertia, and then we need to have the curvature, isn't it? So elastic modulus is given here, and then second momentum, let's consider the cross section here. Then we have a wire cross section. So we have to calculate the second moment of inertia for this wire. And then we need to calculate the curvature. So curvature is what? The curvature is the radius to the center, isn't it? So curvature is the radius. So not, but I mean the radius of the rigid cylinder plus, and then radius of the wire, d divided by 2. And that is the curvature. So once you put this, then you can calculate the bending moment, isn't it, right? By the way, if you put a coordinate like this, then curvature is what? It's a negative or positive? This is downward concave. That's why it's a negative curvature, isn't it? For instance. And then let's try to calculate normal stress. Normal stress is equal to what? Bending moment divided by the second moment of inertia. And then we need to put y coordinate with the minus sign. So here the bending moment we have, but it already has the minus sign, and then it should be divided by the second moment of inertia, and then we can calculate the normal stress in different positions using this formula. So when you calculate, you'd better use the unit of stress for the stress unit. You can use megapascal. Instead of the 200 gigapascal, I want to use 200,000 megapascal. Otherwise, we have to worry about the units. And for the dimension, so typically we use millimeters. These 4 millimeters, and then R naught. This is is given by meters, isn't it? 0.5 10 to the power 3 millimeters. Then it's easier to control the units. And then for the bending moment, we can use Newton millimeter, sorry. For the bending moment, you can Newton millimeter. So let's check the unit. Okay, let's look at this equation. And then unit of bending moment. I'm talking about this equation, okay? The unit of bending moment is given by Newton millimeters. So I want to use this unit. And then divided by the second moment of inertia, millimeter force, okay? And then the distance is also given by millimeters. Okay, then I have square of the millimeters, and then it becomes 2. That's why the unit becomes Newton divided by the millimeter square. This is megapascal unit. Is it clear? Okay. And how about the information of bending moment? The bending moment is equal to the elastic modulus and then the curvature. Here the unit of bending moment is Newton millimeters, isn't it? The elastic modulus, so I told you that we want to use a megapascal unit. So Newton millimeter minus 2. And then the second moment of inertia, millimeter force. Yeah. So it is cancelled, it becomes 2. Oh, by the way. No, curvature, sorry about it. Curvature is not dimensionless. Curvature is 1 over rho. Yeah, 1 over rho is a millimeter. Sorry. Millimeter minus 1. Okay? That's why we recover the unit of the moment, Newton millimeters. Is it clear? Okay. So typically we use millimeters for the length. Okay. And how about the area? The area we use millimeter square. Then we automatically have a megapascal unit for the stress field. Therefore, when you use modulus instead of gigapascal, we use megapascal unit. Okay, so now let's say we have a certain beam problem. Then, as we discussed, the normal stress is linearly distributed in the cross section. Okay, at the neutral axis, normal stress is equal to 0. And then if you check only the magnitude of normal stress, then it is maximum on top and bottom fibers, isn't it, right? So let's check the material behavior. If you want to check the material behavior, for example, let's talk about the concrete, strain and stress. It would behave like this, isn't it? So typically we want to call this is tensile strength, and then this is called the compressive strength, isn't it? So since to guarantee the safety of the cross section, then instead of tensile strength, maybe we want to introduce some kind of allowable strength in tension. and also the allowable strength in compression, isn't it? So what we want to do is we want to compare this compressive stress with this allowable compressive stress, because its magnitude is maximum on the top fiber. And then in the case of tensile stress, we want to compare the tensile stress with the allowable tensile strength value to verify the safety of the cross section, because the stresses are maximum on top and bottom fibers in these linear elastic problems. So maybe we don't have to worry about this change of coordinate system, because we are interested in only the maximum values of the magnitude of the stress. Okay, that's why we wanna instead of using the y coordinate, we are interested in what is the maximum distance. What I mean, measured from the neutral axis. This is the maximum distance to the top fiber, C1. And this is the maximum distance to the bottom fiber, C2. Okay, we can measure in this way. If you put the information of coordinate into these two equations, we can calculate the maximum, the minimum or maximum stress using this formula instead of using coordinate, because we are interested in maximum values. Okay. And then here, if you look at these two equations carefully, we have one internal force, and then we have two the measure of geometry, second moment of inertia, and then distance. Then, because these characteristics of these two are the same, that's why we maybe want to rearrange this equation in this way. For example, the minus m I second moment of inertia divided by the distance, isn't it? Yeah, we can consider it this way, because these two have the information of the geometry of the cross section. Okay, and then simply we call that quantity the section modulus. 단면 계수. The ratio of second moment of inertia divided by the first distance from the neutral plane is called 단면 계수. It is defined this way. The second moment of inertia divided by the first distance from the neutral plane of the cross section. So using this ratio, we can calculate the maximum or minimum normal stress using the formula. We just divide the bending moment by this quantity. Okay, then actually, as I told you, we are not interested in the specific the signs, so we are interested in only the maximum values. If you given we understand whether the stress is negative or positive. So that's why instead of using this, so we, without having the sign of the normal stress, we just simply represent the maximum normal stress by using this formula, the bending moment divided by the section modulus. Okay, actually the definition of section modulus is very informative, and it's convenient, especially when you design structures. So what we do is we just calculate the bending moment diagram for our structure, and then we compare the normal stress development with the material that we want to use, and then we determine the cross section using the measure of cross section is given by the section modulus. Okay, so now let's talk about the design procedure for bending. So first thing that we have to do is, in design procedure, the very first step is we need to calculate the internal bending moment. Okay, internal bending moment. So the last time that we already discussed how to construct the internal bending moment. Let's say we have internal bending moment diagram, BMD. And then we have to determine the allowable strength with the factor of safety for the given material. Like if you want to use concrete, then you need to consider the allowable strength of concrete. And if you want to use steel, then you have to use allowable strength of steel with the consideration of factor of safety. And then we need to calculate the required section modulus. Required section modulus comparing the normal stress corresponding to the internal bending moment. For example, look. So our stress is what? Our stress is should be given by the bending moment divided by section modulus, isn't it? Should be less than or equal to the allowable strength value. That's why my section modulus should be greater than or equal to the bending moment divided by what? The allowable strength. Okay, once you have the information of section modulus, then you just check design handbook for the various cross sections to determine to find a cross section which satisfies this inequality. Okay. Now let's talk about an example here. How many minutes? Okay, I'd like take 10 minutes break before we discuss this example problem, because we need to talk a lot in this example problem. Okay, let me take a 10 minutes break.